Hello class, it's me again, Professor Pat. Today I'm going to be talking about a quick summary of curve sketching. So, let's start talking about a frame of reference. When graphing a function, it normally is not possible to show the entire graph. So, it is very important to decide which part of the graph to show. Let's consider two graphs of this same function f right here. So these graphs denote the same function, but it is very clear that the frame of reference used on the right hand side is better point of view than this frame of reference on the left. So you may be wondering, would a third point of view reveal other interesting portions of the graph? So what we're going to do is we're going to use calculus to find all the information we need to figure that out. So there's 3 steps for analyzing the graph of a function. First step, we got to determine the domain and range. We need to determine any asymptotes, intercepts, symmetry, and end behavior. And we need to use the first and second derivative tests to determine relative extrema and points of inflection. Let's consider this function f of x equals 5x squared minus 9x plus 5 divided by x minus 1. We know our domain is going to be all real numbers except for 1, because you can't divide by 0. I'll leave the range blank for now, but we know we've got a vertical asymptote at x equals 1, no x-intercept, but we've got a y-intercept at 0, negative 5. We've got our derivative is going to be 5x squared minus 10x plus 4 over x minus 1 squared. We set that equal to 0. We get our critical numbers as 1 plus or minus root 5 over 5. We also know that 1 is a critical number because f prime of x does not exist at x equals 1. Our second derivative, f prime of x, is going to be 2 over x minus 1 cubed. Now there's no such x. There's no x such that f prime of x equals 0. However, f prime of x does not exist at x equals 1. So that gives us a possible point of inflection. But because the f of 1 is undefined, we know that this graph has no points of inflection. So what we're going to do with this information that we've gathered now is we're going to test a couple intervals to determine the characteristics of this graph. The intervals and points I'm going to test are negative infinity to 1 minus root 5 over 5, 1 minus root 5 over 5 to 1, 1 to 1 plus root 5 over 5, and 1 plus root 5 over 5 to infinity, as well as x equals 1 minus plus or minus root 5 and x equals 1. Using this graph here, we see that given all these intervals and points, we can use characteristics using the first and second derivative tests to determine the characteristics of the graph, including increasing, decreasing, concave, and concave in which direction. Like I said, this graph has no points of inflection, but there is a vertical asymptote here at x equals 1. So using this information, our graph should look something like this. Yeah? Well, so using calculus, we were able to determine everything that was important to be shown in this graph. However, you'll notice there might be an additional asymptote along this slant line. So to find the missing asymptote, we're going to use long division to rewrite this rational function as the sum of a first degree polynomial and another rational function. The slant asymptote is going to be equal to the line provided by the first degree polynomial. Alright, let's do some long division. We're going to rewrite 5x squared minus 9x plus 5 over x minus 1. We're going to rewrite it again. We're going to simplify that, and that'll give us our slant asymptote is going to be y equals 5x minus 4, denoted by this green line on the graph. You may be able to see it, you may not be able to see it. Pretty simple. Once you understand the steps for analyzing the graph, it becomes pretty easy. So let's try this again. We're going to use the function f of x equals 3x over x squared minus 16. So at our main, x does not equal 4 or negative 4, but it's all real numbers excluding those two. Our range is going to be all real numbers. We've got our vertical asymptotes, like we said, at 4 and negative 4. We've got to recall that the degree of the numerator does not exceed the degree of the denominator by exactly 1. So that means there's no slant asymptote in this one. Our x-intercept and y-intercept are going to be 0, 0. So our derivative of 3x over x squared minus 16 is going to be negative 3x squared plus 16 over x squared minus 16 squared. We set that equal to 0. We get our critical numbers. We know there's no x where f prime of x is 0. However, f prime does not exist at x equals 4 and x equals negative 4, so those would be considered our critical numbers. Now we're going to find our second derivative to be 6x times x squared plus 48 over x squared minus 16 cubed. So f prime of x equals 0 when x equals 0, and it also doesn't exist at plus or minus 4. So because f doesn't exist at plus or minus 4, we know that x equals 0 is the only possible point of inflection. So because f of x approaches 0 as x approaches both infinity and negative infinity, I would hear an argument that there could be a horizontal asymptote at y equals 0 in the interval where where x is between negative infinity and 0, and also y equals 0 when x is between 0 and positive infinity. You can't say there's an asymptote at y equals 0 because f of 0 is equal to 0. So we're going to use these values to test some intervals: negative infinity to negative 4, x equals negative 4, negative 4 to 0, x equals 0, 0 to 4, x equals 4, and 4 to infinity. Boom. Plugging in these values and these intervals, we find at f of x equals 4 and negative 4, we've got vertical asymptotes. At x equals 0, we've got a point of inflection. We can see these values: first derivative test, second derivative test, to determine whether it's increasing, decreasing, concave up, concave down. So all this information in this table right here gives us a graph. Should look something like this. And once you're familiar with the steps, sketching graphs becomes a very simple process. Let's give it a try. One more function. Alright, so the function we're going to do is f of x equals x to the 4th minus 12x cubed plus 48x squared minus 64x. First thing I want to do is simplify. X times x minus 4 cubed. So we know our domain is going to be all real numbers. Our range, our absolute minimum will happen at negative 27. So our range is from negative 27 to infinity. Our x-intercepts happen at 0, 0 and 4, 0. So that gives us a y-intercept at 0, 0 as well. Our derivative is going to be 4 times x minus 4 squared times x minus 1. It gives us our critical numbers of x equals 4 and x equals 0. Pardon me, x equals 1. Our second derivative is going to be 12 times x minus 2 times x minus 4, giving us our possible points of inflection at x equals 2 and x equals 4. Alright, so as x approaches infinity, f of x also approaches infinity, and same as x approaches negative infinity. The end behavior at both positive and negative infinity has f of x approaching infinity. No vertical asymptotes, no horizontal asymptotes, no slant asymptote. So we're going to test some intervals using the information we just gathered. We're going to go from negative infinity to 1, from 1 to 2, from 2 to 4, and from 4 to infinity. We're also going to test x equals 1, x equals 2, and x equals 4. So as you can see, when our first derivative equals 0, but on either side it changes from negative to positive. We know the first derivative test tells us that that point must be a relative minimum. That point is 1, and we know f of 1 is going to equal negative 27. So our relative minimum is, in this case, our absolute minimum. That won't always be the case, but it is in this function. We've also got a point of inflection at 0. When f prime of x equals 0, we know that's a point of inflection. That happens at 0, negative 16, where the function changes from being concave downward to concave upward, or concave upward to concave downward. So we notice this graph has at least 2 points of inflection. We also know where it's increasing and where it is decreasing. So using all this information in the table, our graph should look something like this. You'll notice decreasing and concave up in here, and right around here at 0. Right, at negative 16, the graph changes from being concave down, or being concave up, to being concave down. And here again, where x equals 4, we see this is a point of inflection where f of x changes from being concave downward to being concave upward. Fairly simple. Any questions?